So it's, of course, my great pleasure to introduce Tuya for this colloquium. And I will read the brief bio that I have. That, of course, she joined us in August 2021 in the framework of MA-Care, and she's from the University of Helsinki, Finland, where she completed her PhD in physics and a master in chemistry. After her dissertation, she went for postdoc in California at Irvine, USA for a year, but she was also visiting a researcher in Tropos in Germany, in Leipzig. Before she joined the Cyprus Institute, she was the head of a unit for two ACTRIS calibration centers. So ACTRIS is the European research infrastructure for aerosol clouds and trace gases. So she has been working as the head of this unit in Helsinki, a group leader of a PANDA group that maybe you will tell us more, but it's not anything about animals, it's about polar and Arctic atmosphere research group. So she has a long history on something that we are not good, but now we will become. It's chemical ionization atmospheric pressure interface time-of-flight mass spectrometers. It's a COI Apitow. And she's an expert in this, a world expert in this, accumulating a lot of field observations on aerosol precursors that are below the 10 nanometer particle size. She wants to solve a lot of scientific questions, fundamental science, though not only, but she will be aiming to understand how aerosol particles are formed, considering the condensing vapors in the atmosphere, how aerosols will affect the climate and the ecosystems in our region, the Eastern Med and the Mediterranean. And of course, you know that she has been recently awarded by the starting grant of the European Research Council, the ERC. It's the second ERC of the Cyprus Institute. If you remember, 10 years ago, Joost Lelleveld got one, though it was not a starting grant. And her project is called BAE, and it's the role of base molecules in aerosol formation. And I'm sure she will tell us more today. Tuya.
Thank you for the long introduction. I usually start my presentations by telling a few words about myself, so maybe I can skip that. But yeah, today I wanted to give you an overview of a little bit broader subject that would link different ecosystems or different environments, clouds and climate. And there's a word missing from that, but let's see. So usually, yes, I will briefly go through what I've been doing as well, and then I will give you some introduction to different ecosystems, aerosols that was missing from this link, clouds and climate. I will go through formation studies, how aerosols form and how we can measure them, and I will do some case studies from Antarctica to the Arctic, how trees affect this process, and some really cool specific features that how ecosystems can produce different sorts of aerosols. And then what next is something that Jean already mentioned, is the BAE project as well. So as he was mentioning, my background is at the University of Helsinki. So I did my PhD and my master's at University of Helsinki. Worked with this guy that most of you know, Markku Kulmala, in his group. And then I visited also Tropos in Leipzig with Thorsten Bernd, doing more laboratory studies. I went to UC Irvine in this ultrafine aerosol group for 1 year before joining ACTRIS national facilities. So I was the head of starting to calibrate these instruments more formally. And currently I'm here almost 2 years now, assistant professor at KRC, at AOD. I am trying to do my best with running chaos stations on the island, and you will, oh yeah, okay, let's go forward. So basically we are running these 4 stations on the island. Right now I'm not going to show any data from them yet, but hopefully next time when we see, I will do that. I will start from basics because I don't think that everyone knows the atmosphere really well. And what I'm going to going to talk about. So just very basics from the atmosphere. So let's set our domain. First of all, we are somewhere here in the boundary layer, in this troposphere. So basically, we have a halo. The atmosphere is a halo around Earth, consisting of gases, and within the lowest layer called troposphere, usually the weather and all chemistry happens. It's not usually like within this first 10 kilometers, approximately. And if you think of atmosphere, if you take 1 sugar cube of air, so think of that little amount, it contains this many molecules, so 10 to 19 molecules in 1 cubic centimeter. And you know, if you put it in boxes, this is 100 boxes, this is nitrogen, 78% oxygen, 21 argon, and then there's this little dot here that contains trace gases and particulate matter. So why is it so important? Like, it's tiny, but as we go forward, you can see that small things really make a big difference. There are 2 sets of aerosols. So first of all, let's define an aerosol. It's a solid or liquid particle in gas media. So it can be solid particle that comes out of, okay, this is really weird, of a volcano here. And it could be ash, dust, pollen, sea salt, something like emitted to the atmosphere directly. This would be primary aerosol. And then if we have something, let's say that we have a SO2 coming out of the volcano as well, it goes through phase transition, there's chemistry that happens, and it forms sulfuric acid. And what happens is that it starts forming particles, it starts clustering. And it's about 50-50. If we count particles, every second is primary and every second is secondary in around here. If you go to the Arctic, even more. And then I wanted to say that there are different ecosystems, so different environments can produce aerosols, but because of different reasons. So I've been studying this for like maybe 10 years now. And there are, you know, these are the biggest precursors that I could now think of. The ocean that has, you know, large quantities of phytoplankton and seawater. So there are emissions of sulfur compounds and halogens. Forests emit a lot of organics. We emit, well, what don't we emit? Oh, sorry. Where did it go? I'm pressing this one. So yeah, what don't we emit? We do everything, nitrogen-containing compounds, sulfur compounds, organic halogens, you name it. And then we get from farming, the biggest constituent is nitrogen-containing species. And all of these have kind of different roles in aerosol formation. And what I mainly do is I study, you know, you just saw those emissions. Then there's this great box called atmospheric chemistry that happens that starts creating these condensing vapors. So usually it's an oxidation process that starts getting more oxygen into these molecules that makes them less volatile and kind of sticky. So they want to stick together and kind of group together. If they don't evaporate, they start nucleating, forming these 1 to 10 nanometer particles. They start growing, and they can form these particles that can already be cloud condensation nuclei, grow water on top of them, and actually affect the climate. And so why on earth would we want to kind of study aerosols? So I put this coffee cup here because this is a good example of the role of aerosols. So you have this hot cup of coffee, and as I'm saying, without aerosols we wouldn't have clouds. So if we didn't have particles where the water condenses on, we wouldn't have this, we wouldn't see this. So if you go to Antarctica and you take your mug out, there's no cloud on top of it. So small things are really meaningful in that sense, and this is a really great example. Aerosols can affect climate directly by scattering or absorbing solar radiation. They can also have indirect effects in modifying cloud properties. So they can harm your health because you inhale them, they can go into your bloodstream, and they can cause some risks like cardiovascular or lung cancer that can be bad for your lifetime. And I want to wake you up at this point with a little calculation. So as I said, these things are tiny, like nanometer scale, and they grow slowly. And they grow into the clouds. So how much do you think that a cloud weighs? Let's say that it's a cumulus cloud. It has 1 kilometer every direction. Any guesses? So I can drink a sip of water here. Okay. What would be the density be? It's approximately 0.5 gram per cubic meter. So if you divide or multiply that with the size, the volume of it, it's actually quite heavy. So small things matter. And you remember the Gallians? I don't know if you read this when you were kids. They feared that the sky is going to fall on you. This is very real. So let's go back to climate. As a source of error in this radiative forcing, it's still said, this is not the updated version, but if you look at every single bar, how they affect the radiative forcing, if you look at aerosols, we have really large error bars. And usually this is because we don't really know well how aerosols form. It's very difficult to measure. And the challenge really, it's real. So as I was mentioning, 1 cube of sugar already has 10 to 19 molecules. Now take a pen, that's 1 cubic millimeter. It contains this many nitrogen molecules, oxygen, carbon dioxide, sulfuric acid that can start forming particles, 1,000, and then one of these clusters. So this is like the diameter of your hair, compare it to the distance to the sun from Earth. So this is like really, we struggle with real problems that the concentrations are so low, it's nearly impossible to detect these things. But that's why we have departments like KRC, that we have good funding and resources to start studying things like this. And what I've been using for the last about 10 years is, you see the bar, wow, this is really something. So you see the bar behind, it's from gas to little particles, 1 to 4 nanometers in size, then a little bit bigger and all the way up to CCN sizes. So the instrumentation that I use to measure these things is a mass spectrometer. This is like my baby. I use these different chemical ionization methods to charge neutral molecules and detect them then. Then we use this, okay, this is not working as it should. So then we use these condensation CPC, so condensation particle counters. So basically they work the same way as the coffee mug. You condense something on top of a particle and then you optically measure it. And then air ion spectrometers. And then let's go and see how formation of aerosols is linked to different ecosystems or different environments. So this is case Antarctica, and how penguins, supernova explosions, and a bunch of scientists in Antarctica have something to do with bananas. And some people know what a banana is, but it is this guy here. So you have a particle size distribution. This is the size of a particle. This is the time, and the color is how many particles you have. So you start from small particles, and over time you grow them. So bananas. Case Antarctica really is like studying pre-industrial era. There are not a lot of emission sources, very few, some of course. And there are really good reasons why to study Antarctica. It's also in the southern hemisphere, So we have very little mixing from the northern parts. And usually climate models need a baseline, so you have to start from somewhere. So if we study these processes, maybe we can get this kind of idea how the atmosphere was functioning in the pre-industrial era. So we can just cross these. And this is how it looked like. This is already 10 years ago, 2014, 15, when me and my former supervisor, this is Mikko Sipilä standing there. So we went to Antarctica. This is the Finnish base called Aboa. It's a continental site or coastal site, but it's on a continent, it's not on sea ice. And this is our 900 kilos and about €1 million worth boxes all around Antarctica. And we were measuring cluster chemical composition, ions, precursor vapors, and different diameter particles from this container. And what we observe is we had to wait for a month. It wasn't like we waited for a month, nothing happened. And we were like, okay, everyone says that, you know, in pre-industrial times, the nucleation of, or the secondary formation of aerosols is like, okay, 90% of all particles form this way. And we didn't see anything. And then we were at midsummer and we started seeing these. These are not so pretty bananas as I showed you before, but all these 4 days are new particle formation events. And then we also saw, this is the chemical composition. We have sulfuric acid, another sulfur-containing compound called methane sulfuric acid, and then iodic acid on here. So at the same time, when we see this particle formation event, we see a lot of sulfuric acid in the air. And this actually equals, I don't know why it doesn't say anything, but the maximum concentration equals like 1 ppt, 1 to 2 ppt, so parts per trillion. So it's very, very low concentration. For me, it's high, but to the rest of the world, it will be very small. So what are the particles made of? Because we had mass spectrometers, we can detect the elemental composition of those. And so this is what it looks like before the event, 3 hours before. So you have 1, 2, 3, 4, 5 sulfuric acid molecules. This is like a mass spectrum presented in a way. You don't have to know the details, but sulfuric acid goes, like addition goes this way, and if we have ammonia, we would go towards the positive side. And this is what happens when we have a particle formation event. So we see all these dots appearing in the spectrum, and it seems to be that it's clean, pretty clean, sulfuric acid, ammonia, and probably water nucleation. This was one of the first experimental results to actually observe this phenomenon. And what we also could see that they were all ions, so we didn't have to charge them, they were already ions. So the only ionizing radiation present is from galactic cosmic radiation, there's no radon, and so it has to be that it was somehow related to ionizing radiation. And there was lots of sulfuric acid and ammonia in the air. And we were like, okay, where's the ammonia? Like, we don't have any sources here. And how does this relate to climate? So, okay, actually I go to this first, then I come back. So what was the source of the particles? Was that every time, this is the sea ice cover, and these are the air masses that we looked back on, and every time we had a new particle formation event, we got these open ocean air masses. And open ocean has phytoplankton that emits this guy called DMS, dimethyl sulfate. It oxidizes into methane sulfuric acid, and in the presence of sunlight, also to sulfuric acid. And this could explain most of the observations. And the ammonia. So there's a penguin colony right about there. And that's like the only thing that we could figure out what it is. And I know from later experiments in the area that they are really, really big. You can smell them. This is a good detector for ammonia. So, but you can smell them. But for the ammonia to travel about 350 kilometers, it's like on the limit of its lifetime. So we think that was it. And how does it relate to climate? So this was supposed to be this next slide. So there are these hypotheses that if the ocean temperature increases, we would have more production of phytoplankton that would produce more of this DMS that will be emitted to the air, that would produce more sulfuric acid and MSA that can then nucleate and form more particles. And then we would form more cloud condensation nuclei and reflect more radiation into space. We measured some parts of this, not everything. Of course, there is an anti-version of this. So what happens if the water gets so warm that all the plankton dies, then there's no CCN forming anymore. So there are multiple, okay, we can only measure puzzle, pieces of puzzle, but not all of it. But basically, case Antarctica is that phytoplankton is a major contributor to this coastal formation of bananas. So then if we go from Antarctica to the Arctic, these are these really easy access studies. So we study polar regions because, the temperature is rising like crazy. And there is a rapid sea ice loss, acidification of the ocean, stratification, winter temperature rises. So we went there as well. This is Svalbard, so on top of Norway, there's this group of islands. There is a little village called New Ålesund. We have a lab here. University of Helsinki is still doing some measurements in Svalbard. And the banana formation is very, very frequent on the islands during the spring. And they effectively seem to be forming CCN-sized particles by condensational growth. And so we wanted to go there and see what was going on, like, okay, is it sulfuric acid that's growing the particles? Is it something else? And with help of some other scientists, biologists, we were able to catch this DMPS, which is a precursor for DMS, and chlorophyll concentration in seawater. So they go pretty well with our observations with sulfuric acid and MSA in the air, but we can't really follow this throughout the year. But we could also see that, okay, this is the diameter again, so this is the size distribution plot in the back, and then if you plot these things on the top, you can see that during these high particle number events, you get these peaks of MSA as well. So we suspect that MSA is growing the particles in the Arctic. So it's a little bit different process. We also did some measurements in Greenland. The chemistry is a little bit different. I will come back to it later. But in Greenland, we don't get any particles because it's so covered in ice most of the year, so we don't really get CCN-sized particles. In New Ålesund, in Svalbard, we do get the CCN-sized particles that they can be affecting the climate in the area. Then about forests. Forests are, they emit tens of thousands of VOCs. So can they be somehow connected to this process? It seems that climate models are not very good. They're getting better at predicting aerosol formation and growth over forested areas. And initial clustering of the compounds starts from sulfuric acid again. So, for example, we've been doing a lot of studies with the University of Helsinki at the SMER2 stations and now also here at the COW station, how these organics affect aerosol formation. So, SMER2 station, you saw these plots before. All the dots were here, very different kind of picture. Now we have these green patterns here that are all organics. And for the last 5 years, we've been doing a lot of studies to identify these peaks. And these can be very abundant in the Arctic in the future because the climate change is it's just going up, and we get more and more VOC oxidation products in the north as well. So do these compounds do anything? So we went to a chamber, we put seed particles in it. So this line is that you put seeds. You put little particles in the chamber. You start producing these organic compounds, and you see that they actually do. So the signal decreases. This means that they are going and condensing on the particles. And actually, what we see also here that the process is irreversible, so they don't evaporate. So organic material definitely grows particles bigger in size. Then there's one last thing. In the Atlantic coast, there is a completely new type of way to form particles. So, I don't know, you can buy these kelp pills because they contain iodine. And this can help your thyroid. So when you go to Atlantic coast, this is Mace Head in Ireland, and we see that we don't get bananas, we call them apples. I don't know, we like our fruits. So, and what we see during these events is like, okay, we see a little bit of sulfuric acid, but what we see iodine containing species. So iodine is actually coming out of these kelps during low tide, and when sun hits the kelp forest, okay, yeah, that's soon. So when the sunlight hits the kelp forest, it releases iodine that oxidizes into these iodic acid species that are depicted in here. And this is the first paper that ever recorded neutral nucleation. So we had to charge these compounds, and we could follow nucleation one by one. And we were so confident of this discovery that if we go to Mace Head and measure this, that it's going to be a Nature paper. So this champagne was bought on the way from France. And this is us. This is the three first authors, Mikko Sipilä, Niina Sarnela, and me, drinking the champagne after we recorded this. It took a few years. In 2016, it was published in Nature. But it was a pretty cool discovery. So what next? We already know, we know acids form particles, we know organics form particles, everything forms particles, and it seems pretty solved. But, so the ERC project that was just started 3 weeks ago is studying the role of base molecules in the process, because the acids don't nucleate without the presence of a base molecule. And we don't really have good methods how to measure them. We have methods, but not something that will be consistent and low enough concentrations. So it's my job now to answer that, how we can measure these low quantities of bases. And that's a very short summary of what I just said. But you can just say that even the most pristine atmosphere is chemically very complicated. We really need to have long-term observations to detect changes. The type of the ecosystem, definitely the environment affects how aerosols are formed in the area. And very many parts of the actual ecosystem, atmosphere interface, are not known because people don't talk to each other. And multidisciplinary approaches are definitely wanted and needed. And yeah, I don't know, I was first engaged and then married to this study, but I think now it's a little bit complicated. And thank you for your attention. This is what I just said. So this is your take-home message, and thanks for the attention. And of course, if there are any banana-related questions, I'm happy to take them.
Banana questions?
Apples.
Max?
Thank you for the very interesting presentation. It is a banana-related question.
There you go.
Is it understood yet why iodine leads to the continuing formation of those very small particles, whereas under VOCs or sulfuric acid, the small particles stop forming and grow? which leads to that banana instead of the apple?
Well, there is something that we did not publish from MACED, was the iodic acid plus organics. So the iodic acid nucleation that I just showed you is purely marine air masses. But there are cases when the wind direction changes and it comes along the coastline and it wipes, these grassy fields. And we definitely get growing particles. But I don't know why iodine itself doesn't, like there's some energy barrier or steric, I don't know what it is, but they don't really grow. They just create a lot of particles that don't really grow. But organics grow those too.
When we breathe in, we're breathing about, every time we breathe in is about 1 liter of air. So how many of these particles do we actually breathe in? And if anybody calculate how many we actually breathe out?
I have no clue how many we breathe out. Maybe, Jos, have you done anything like this before? But of course, it depends. We have the particle size distribution measurements and the total number concentration in Agia Marina, not here on the campus. But we can definitely tell you how many particles you're breathing in all the time. We even have a web page to tell you that. So it shouldn't be too hard to count.
Yeah, okay, we are going a little bit into medicine, but one of the biggest problems in medicine is what is known as endocrine disruptors.
Okay.
Yeah, these are molecules that go into your body and they are competing one way or another with the hormones. And the hormones are having an effect in a minute quantity, so if you disrupt them a little bit, the effect is... So I just, by listening to you now, it came to my mind that this is a huge area of potential interest because it's a major medical problem. One is, of course, what we eat.
Yes.
The other one is because these are small molecules and they can easily mimic their effect on the receptors of the hormones. So that's
You're right.
That's a serious problem. So it would be nice to see how many we're breathing in, at least how many we breathe out, how many they stick.
Yeah.
At the very least.
But the thing is that, it is a little bit difficult to if you assume that everything condensates, like we now do, that they are low in volatility, it basically means that you meet any surface, even the inlet tube. The process is irreversible. So you condense and you stick there. So in that sense, I would answer that all of these condensing vapors stick to a surface. I don't know how deep they go, or if they do. I think it has something to do with if they're hygroscopic or not. Some of them are not, so they might be. But the numbers I can give you, like how many particles of certain sizes we have. And it's also the size, it's the composition. Franco.
Thanks, Tuija, for this fascinating talk. I was wondering one question, actually. Most of these studies are done usually at the surface of the Earth, because that's where the biggest sources of gases and aerosols are, and also because it's we need heavy equipment to do the studies, and it's hard to do them in altitude. But is there any, do we have any studies of particle nucleation at altitude? That we could have some sources. You showed the volcano, for instance. So are there any studies, or how would you go about to do it at altitude?
Yeah, there are some studies, of course, but done from planes. And I'm not sure if they put the Apitov in a Zeppelin, this air vessel. But definitely there are even from the Helsinki group, they own a little Cessna plane. So they did some measurements because as you said, the instrumentation, it's about 100 kilos. So, and it needs more, usually it needs an operator a little bit. So, and one of the problems is, again, the condensation in the inlet tube. So if you have these, you know, these experiments that they fly these commercial planes, and they have this rack of instrumentation inside the plane. But the inlet lines are very long. So we can't afford to lose, we would lose all the condensing vapors. So you can do, and you know, small nanoparticles you also lose to the walls usually. So you have to have very short inlets. And then the pressure that we do, the charging in atmospheric pressure also. So the pressure differences are a bit tricky. But there have been studies on small planes, definitely. And there is, I think University of Frankfurt has this one instrument that is put on like commercial planes even, like, or higher altitudes. But I'm not very, I don't know much of the higher altitude measurements. Of course, we have been to mountaintops on the Mount Everest base camp, that's the highest. And then there are studies on the Andes, the mountain range, up to 5 kilometers. It's mostly because I hate flying, and I would be so seasick on the plane that I refuse to do those. So you can ask someone else. Okay.
It's more a comment than a question. Is that back 30 years ago, I was doing my military service close to Antarctica, and I was measuring DMS, your famous compound there.
Yes.
And then I was going every day with a backpack doing 3 kilometers to fill the bottle of air, and going 3 kilometers back and switch on my GC. And it was taking me 3 hours to get 1 point of data every day. And it took me a year for every day of the year doing this. And then 30 years after, or 20, 25 years after, you bring with a ton of equipment and you get measurements of 10 times more compounds every second. And I'm telling myself what I have done to contribute to 1 point every day for a year, where you can get so much so fast. And it's just a comment that I have always, the kind of, when I'm hearing this type of presentation, for me it's a bit science fiction. How far we can go in the technology to detect these clusters that we were not even aware 30 years ago, that to explain the full story you need to go to so small to go to so big impact.
Yes.
So.
Yeah. And it just keeps getting worse, better and worse at the same time, because now we have these multiple ion source inlets that I can put 6 different chemical ionization units in one. Change the polarity fast, like within 1 second. The amount of data that we just produce, like, you know, think of measuring for 1 year, like how many data points, how many gigabytes, how many terabytes of data that is, to get someone to sit there and even start to look at it. It's also very difficult for the students to comprehend when you start from here, that you didn't do that 1 point measurement, that you slowly kind of gather this information. So it is very complicated. And I think the technology has really, really developed within the last 10 years, like, because I have the first CI Apitow paper, and that was published in 2012. It's only 10 years ago. And now we're doing this, so we still are lacking a lot of those field measurements, so I think you did a pretty good job, because people want to go in the lab and do easier studies.
Yeah, so I think there is no more questions.
Yeah.
I would like really to thank you, Priya.
Thank you.